All right, well, good morning and good afternoon, everybody. We're here with period one. Period one, you want to say hi? All right. So, we finished up the last notes we talked about where we finished up with showing periodic tables, defining what the periods and the groups were. So now we're going to go to Roman numeral. Now this is a continuation from the periodic table. I'm going to call this Roman numeral 6. So we're continuing on from the last set of notes. And real simple, let's see. Atoms, you might want to abbreviate atoms with an A, have up to 7 shells. And that's directly related to the number of periods on the periodic table. Let's zoom that in. So somebody's watching this at home, they can actually see it. Okay, so I got to stay between the red lines. Didn't do a good job there. Okay. Now, these shells can be called, they can be called shells. They can also be called orbitals. As atomic theory evolved, they went from the idea of a shell to there's different shells, and then when they started to realize there was different amounts of energy to hold an electron in, they called them energy levels. You'll hear that. And then they'll maybe even call it the electron cloud. I abbreviate electron with an E negative, electron cloud. And if you need to, it's always good in a new set of notes if you're not used to it to put little, when you do abbreviations, to define them. So let's see. We're going to draw a Bohr model, B-O-H-R, named after Dr. Niels Bohr. And the Bohr model, I think we already did an activity with that in our class. Probably we did, those of you watching the notes. But let's take the element, let's do beryllium. We'll draw the nucleus for beryllium. And we look on the periodic table. This is probably a bad periodic table. It's got atomic number of 4 and a mass of 9. So we're going to put that it has 4 protons, and for neutrons, 9 minus 4 is going to be 5 neutrons. It is in period 2, so it has 2 shells. So we can go ahead and draw, I'm just going to do partial shells. It has 4 protons, so before it does chemical bonding, it's going to have 2 electrons attracted to it, which will fill up the first shell, and then it'll have 2 electrons out here in the second shell. So we could say that it's valence electrons. It has 2 valence electrons. 2 valence electrons. So that's a term that will come up a lot. The number of outer electrons you have, that's your valence electrons. So let's see, moving on. Just a simple reminder when we do this, the first shell, up to 2 electrons. Second shell, up to 8 electrons. Third shell, okay, technically it's up to 18, but 8 fills in first. So when we draw Bohr models, we're going to say that we fill electrons 2, 8, 8. Because what's going to ultimately happen is once you start adding a 9th electron in here, it's going to actually start filling the 4th shell. Yeah, I know, it's great that it does that. So let's move on. I don't want this to be too long. So atoms want outer shell to be full, which means 8 electrons. All atoms want to do that. This is what drives chemistry. And most atoms on the periodic table do not have 8 electrons in their outer shell. The only ones that do are these guys right here, the noble gases, the inert gases. everybody else on there, all the rest of the hundreds, they want to either get electrons or lose them. And it becomes this really interesting tugging match, shoving match, or a sharing match. So these are the noble gases, also known as inert, completely unreactive. All of these need more or less electrons. Sorry, I kind of slopped that out there. All of these need more or less electrons. Hydrogen, for example, it's got 1 electron. So this is not full. Hydrogen and helium want to have 2 electrons. So this would be said to be unstable. Okay, wait. Shell, outer shell, not filled. So it's unstable. Or you could call it very reactive. And all the elements in group 1 have that 1 electron out there, and they want to get rid of that so bad, they will do anything they can, including bang explosions. They throw them in water. You throw pure, all the rest of those in water, they're going to explode. Because they want to get rid of that 1 stupid electron. Because if I can get rid of this 1 stupid electron, hey, wait a minute. If I'm hydrogen and I get rid of that 1 stupid electron, my outer shell is empty. Sorry. So, atoms want their outer shells either totally full or the outermost shell totally empty, and that will make them stable. So, let's take a look at our friend helium over here. Helium has 2 electrons. Helium, its outer shell is totally filled. So, outer shell full. Okay, we call that stable. We could call that inert. We can call that unreactive. Helium, I think I misspelled reactive, sorry about that. Helium and all of the noble gases are completely stable. These all have 8 electrons in their outer shells. They don't need to get rid of them. They hold on to those really tight. So for the rest of the rabble on the periodic table, as we drew, okay, I'm going to have to do this. We should have just done, or if we have not, this is a diagram showing the outer electrons in each of those. All of these elements do not have 8 electrons in their outer orbital here. These guys over here are going to tend to steal electrons because they just need like 1 more over here. These guys over here are going to throw them away to get rid of them. Okay, I think we're just about done. Oh, here we go. So now we're going to get to Roman numeral 7. So I kind of talked about that. Periodic trends. And this is review, and then I'll stop this for a moment. And that's where it'd be really nice to get this chart right here out. And you can tape this to the side, you can tape it over here, but these are the trends that you were supposed to have learned in 8th grade. And oh darn, I forgot to print these up. Oh, that makes me mad. Okay. So, just going to fill them in here, and I'll show you the diagram later. So, on this, what we got here, we've got, this is going to be for density. This right here going across this way is going to be atomic number. Oh, I take that back. This is the group. So, we're going from group 1 to 18. No, you need to take notes right now. So, the density right here, when you look at the periodic table, what you're going to see is, let me get another one here. Okay. I can find one because I want to draw on it. There we go. Let me zoom out right here now. So for density, as you look at the periodic table, what tends to happen, the elements in the middle are very dense, the elements on the side are very low density. So what happens is, if I make a graph of the periodic table, this is group number coming across this way, and this is density for the first one. The elements in this group have really low density. The elements near the middle of the periodic table, and actually we got to include that one, are going to be fairly high. And then as you get to this side of the periodic table, the densities get really low. In fact, these guys are gases. So what happens is the trend for density on the periodic table is low on the ends and high in the middle. So let's draw that. That's the first trend right there for density. That tends to happen. The next one, hardness on elements. So on periodic table, if you can measure their hardness, this same trend is going to tend to occur. The elements in the middle tend to be hard. These tend to get softer off to the side. These become nonmetals, they're brittle, and then these are gases. So we've got the same trend. Group 1 has a very low hardness, and then it tends to come up like this. Boiling point, the same thing happens. Elements on the side have low boiling points in group 1 or 18, and they tend to get higher like that. Melting points, the same thing. These elements over here on the side, really low melting points. In fact, these guys are already melted. They're gases. In the middle, it takes, these have a really high, these are metals right in the middle. We get this. Heat conductivity, the same thing happens, but this one's kind of interesting. It goes up, and then, boom, there's a spike, and then it comes down. Same thing for electrical conductivity. Goes like this, boom, there's a spike, and it goes down like that. So, these right here, by the way, tend to be the elements that are copper, silver, and gold. And electrical conductivity, copper, silver, and gold. And that ends this first part right here, so I'm going to hit stop on here. Goodbye, everybody. Okay, I'm hitting the wrong button again. All right, okay.